Hello everyone, and welcome to our presentation. I'm Matthias Mendita, joined by Guangyu Sun and Chen Chen. Today, we're excited to share our research titled, Navigating Heterogeneity and Privacy in One-Shot Federated Learning with Diffusion Models. We've delved into the potential of diffusion models for one-shot federated learning, addressing key challenges of privacy and system diversity. Stay tuned as we unravel our pioneering approach, FedDiff, and its implications for the future of federated learning. Moving on to the key highlights of our research, our primary motivation was to address two significant research questions in one-shot federated learning, or FL. We aim to explore the potential of diffusion models, or DMs, for one-shot Florida. We also wanted to study privacy in state-of-the-art, or SOTA, one-shot Florida. Now, let's talk about the problem statement. We found that existing methods do not adequately address model heterogeneity in real Florida systems. This is a critical issue as it can significantly impact the performance of the global model. Additionally, we noticed that privacy concerns are not thoroughly addressed in current one-shot Florida approaches. This is a significant gap, given the importance of privacy in Florida settings. In our research, we have strived to address these issues and contribute to the advancement of one-shot Florida. Stay tuned as we delve deeper into our approach and findings. Moving on to the key highlights of our research. Firstly, we underscore the critical role of privacy in one-shot federated learning. It's not just about training efficient models, but also ensuring that the privacy of these models is safeguarded before they leave the client. Secondly, we identify a significant area for improvement: the quality of data generated under privacy constraints. While our method has made strides in this area, there's still work to be done to enhance the effectiveness of this data for global model training, all while maintaining privacy. Lastly, we spotlight the importance of diversity and fairness in the data used for federated learning. It's crucial to remember that biases in local datasets can lead to unintended algorithmic biases and discrimination in the resulting models. Therefore, ensuring a diverse and fair dataset is a key step towards mitigating these risks. These insights form the backbone of our research, and we hope they inspire further exploration in this field. Moving on to the key highlights of our research. Our work presents a pioneering effort in utilizing diffusion models, or DMs, for one-shot federated learning. We propose a novel method, FedDiff, that leverages the unique advantages of DMs, such as high sample quality and diversity, to enhance the overall performance of one-shot Florida. But we didn't stop there. Recognizing the challenges posed by harsh differential privacy conditions, we introduce Fourier Magnitude Filtering. This innovative solution boosts performance by eliminating low-quality samples, ensuring that only the most relevant and high-quality data is used for global model training. These contributions mark significant strides in the field of one-shot federated learning, and we're excited to delve deeper into these topics with you. On this slide, we delve into the key highlights of our research. Our main proposition is FedDiff, a novel method designed to operate within the one-shot setting. This method significantly reduces the chance of eavesdropping, thereby enhancing privacy. Furthermore, FedDiff generates synthetic data from client models, which is then used for global training. This unique approach allows us to accommodate system diversity, making our method adaptable to a wide range of settings. Lastly, we've tested our method using the CIFAR10 dataset, a popular choice in the field, to ensure the robustness of our results. These highlights underscore the innovative and practical nature of our work. In this slide, we're highlighting some key results from our research. Our FedDiff approach has shown promising potential in enhancing overall performance and addressing heterogeneity in diverse settings. This is a significant step forward in the field of one-shot federated learning. However, we also identified a challenge. Under differential privacy constraints, the quality and effectiveness of the generated data for global model training can be compromised. This is an area that requires further exploration and improvement. These findings are crucial in guiding our future research directions and refining our methodologies. Let's delve into the heart of our research. Our aim is threefold. First, we address two pivotal research questions in one-shot federated learning, or FL. Second, we explore the potential of diffusion models, or DMs, for one-shot Florida. We believe DMs offer unique advantages that can enhance performance and tackle heterogeneity across diverse settings. Our pioneering effort in this direction is the FedDiff approach, which we'll discuss in detail later. Lastly, we study privacy in state-of-the-art one-shot Florida. We contribute a thorough investigation under provable privacy budgets and address memorization concerns. Now, let's take a look at the figure. It provides an overview of the FedDiff approach for one-shot federated learning. The process begins with training a class-conditioned diffusion model on local data at the clients. After training, the local diffusion models are gathered by the server, where they are used to generate data that forms the global training data. The global model is then trained on this synthetic dataset. This approach allows us to leverage the strengths of DMs in a one-shot Florida setting. In the following slides, we will delve deeper into these topics. Stay tuned. Begin a frame. Frame title: Diffusion Models and Federated Learning. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A SRC task underscore execution extracted underscore paper underscore data 2405.01494v1 figures 2405.01494v1 figure 2:2.png captiona tinea. The generative learning trilemma showing the trade-off between sample quality, diversity and fast sampling. Diffusion models excel in sample quality and diversity, making them ideal for one-shot federated learning. End of figure. Begin itemize. Item diffusion models in one-shot Florida. Begin itemize. Item diffusion models offer high sample quality and diversity. Crucial for one-shot Florida. Item: the simplified objective of DMs helps achieve superior performance in complex Florida environments. Item: our FedDiff approach leverages these strengths of DMs in one-shot Florida. End itemize. Item: privacy in one-shot Florida. Begin itemize. Item: privacy is critical in Florida, and our research addresses this with provable privacy budgets. Item: we propose Fourier Magnitude Filtering to enhance performance under harsh DP conditions. End itemize. End itemize. End frame. On this slide, we introduce our proposed method, FedDiff. This innovative approach leverages the unique advantages of diffusion models, or DMs, in one-shot federated learning. The process begins with training a class-conditioned diffusion model on local data at the clients. After training, these local models are gathered by the server, where they are used to generate synthetic data. This synthetic data forms the global training dataset, which is then used to train the global model. This approach not only generates synthetic data from client models for global training, but also effectively addresses the problem of model heterogeneity in real federated learning systems. The figure here provides a visual overview of the FedDiff approach. This method is a pioneering effort in the field, and we believe it holds great potential for enhancing the performance of one-shot federated learning. On this slide, we're introducing our novel approach, FedDiff, for one-shot federated learning. As you can see in the figure, the process begins with training a class-conditioned diffusion model on local data at the clients. After training, these local models are gathered by the server, which then uses them to generate data that forms the global training dataset. The global model is subsequently trained on this synthetic dataset. In addition to FedDiff, we're also proposing a technique called Fourier Magnitude Filtering. This technique is designed to enhance performance under harsh differential privacy conditions by eliminating low-quality samples from the generated data. This ensures that the global model is trained on high-quality, diverse data, leading to improved performance. Let's delve deeper into the FedDiff approach for one-shot federated learning. As you can see in the figure, the process starts with training a class-conditioned diffusion model on local data at the clients. These local models are then gathered by the server and used to generate a synthetic dataset for global model training. Now, let's talk about privacy, a crucial aspect of one-shot Florida. Our approach not only proposes measures to safeguard privacy, but also addresses previously unaddressed privacy concerns in current one-shot Florida methods. This is a significant step forward in ensuring the security and confidentiality of data in the federated learning environment. Let's take a closer look at the FedDiff approach for one-shot federated learning, as illustrated in the figure. This process begins with training a class-conditioned diffusion model on local data at the clients. After training, the local diffusion models are gathered by the server, where they are used to generate data that forms the global training data. The global model is then trained on this synthetic dataset. As we move forward, there are two key research directions we aim to explore. First, We want to improve the quality of the generated data while maintaining privacy. This is crucial to ensure the effectiveness of our model. Second, we aim to ensure diversity and fairness in the data used for federated learning. This is to mitigate risks of algorithmic biases and discrimination, ensuring our model is fair and unbiased. These directions will guide our future work in enhancing one-shot federated learning with generative models. Begin a frame title related works, begin itemize, item overview of one-shot federated learning, Florida and its current challenges, begin itemize, item 1, shot Florida reduces communication requirements by limiting client-server interaction to a single round. Item challenges include high data heterogeneity and privacy concerns. End itemize, item exploration of existing solutions and their limitations, begin itemize, item distillation approaches use an ensemble of client models to create a global model, but often require a public dataset. Item generative adversarial networks, GANs, have been used to generate data for distillation, but struggle in heterogeneous environments. Item conditional variational autoencoders, CVAEs, have been used in highly heterogeneous one-shot Florida, but exhibit suboptimal sample quality and do not address privacy constraints. End itemize, end frame, Let's delve into the current landscape of one-shot federated learning. This approach is attractive as it significantly reduces communication overhead by limiting client-server interaction to just one round. However, it faces challenges, particularly with high data heterogeneity and privacy concerns. Several solutions have been proposed. Distillation approaches, for instance, use an ensemble of client models to create a global model, but they often require a public dataset. Generative adversarial networks, or GANs, have been used to generate data for distillation, but they struggle in heterogeneous environments. Conditional variational autoencoders, or CVAEs, have been used in highly heterogeneous one-shot Florida, but they exhibit suboptimal sample quality and do not adequately address privacy constraints. As we move forward, we'll explore how our work addresses these limitations. Moving on to related works, we delve into the use of generative models in one-shot federated learning, or FL. These models are trained on client devices and then used to synthesize data for global model training. This approach eliminates the need for the challenging reconciliation process that discriminative models require. The synthesized data can significantly enhance the performance of the global model, making generative models a promising avenue in one-shot Florida. This is a key aspect of our research, and we'll be exploring it further in our study. Begin a frame title related works, begin itemize, item in the realm of generative learning, there's a trilemma we often face: balancing sample quality, diversity, and fast sampling. Now, diffusion models, or DMs, stand out in terms of sample quality and diversity. They may not be the fastest when it comes to sampling, but in the context of one-shot federated learning, or FL, this isn't a major concern. Why? Because the sampling can be done offline at the server. So, the strengths of DMs align perfectly with the needs of one-shot Florida, making them a promising avenue for exploration. End itemize, end frame. Begin a frame title related works, begin itemize, item. We've seen that CVAEs, while excellent in diversity and fast sampling, fall short in sample quality. This is a significant limitation in one-shot Florida where high-quality samples are crucial. Item. Now, let's turn our attention to diffusion models. These models have a simplified objective, which could be a game changer in the challenging Florida environment. They excel in both sample quality and diversity, making them a promising candidate for one-shot Florida. End itemize, end frame, Moving on to our related works, we delve into the strengths of diffusion models, or DMs. These models are particularly promising for one-shot federated learning due to their high sample quality and diversity. This means that they can generate a wide range of high-quality samples, which is crucial for training robust and versatile models. Unlike other models, DMs do not prioritize fast sampling, which is not a concern in one-shot Florida as the sampling can be done offline. This unique alignment of DM strengths with the needs of one-shot Florida makes them a promising approach for this setting. In the next slide, we will explore this concept further, discussing our novel approach, FedDiff, and how it leverages these strengths of DMs. In our exploration of related works, we've drawn a comparison between CVAEs and diffusion models, or DMs. The key difference lies in their objectives. CVAEs aim to learn both the encoding and decoding processes simultaneously, which can be quite complex. On the other hand, DMs have a simplified objective. They only need to learn how to denoise a small step in the generation process. This simplicity could be a significant advantage in the federated learning setting, where we deal with challenges like data heterogeneity, class imbalance, and limited sample sizes. So, in essence, DMs might offer a more efficient and effective approach to tackle these challenges in federated learning. Begin A-frame. Frame title our related works. Begin itemize. Item, we've discussed the importance of privacy in one-shot federated learning and how differential privacy, or DP, is used to ensure it. DP introduces a certain level of noise to the training process to protect individual data points. However, this noise can make optimization more challenging. Item, these challenges brought about by DP, such as the added noise and increased optimization difficulty, are significant. But here's where diffusion models, or DMs, come into play. Their simpler training paradigm could be a game changer in these settings, offering unique advantages. End itemize, end A-frame, Begin A-frame. Frame title our related works. Begin itemize. Item, our research addresses the limitations of existing one-shot Florida methods, particularly their struggle with model heterogeneity and privacy concerns. Item, we found that these methods often falter under high heterogeneity, leading to significant performance drops. Item, our pioneering work with diffusion models in one-shot Florida, FedDiff, offers unique advantages, enhancing performance and tackling heterogeneity across diverse settings. Item, we also delve into privacy in one-shot Florida, providing a thorough investigation under provable privacy budgets and addressing memorization concerns. Item, despite these advancements, we acknowledge that our method has limitations, particularly in the quality of data generated under DP constraints. Future work will focus on improving this aspect. End itemize, end A-frame. Moving on to our proposed research and technical details, let's take a look at this figure. This is a qualitative comparison of original training samples and generated samples under a privacy guarantee of E=50. What's remarkable here is that there's no blatant memorization, which underscores the robust privacy measures in our approach. Our research primarily focuses on two key areas. First, we delve into the potential of diffusion models for one-shot federated learning, or Florida. We present FedDiff, our pioneering approach that leverages the unique advantages of diffusion models to enhance performance and tackle data heterogeneity across diverse settings. Second, we address privacy concerns in state-of-the-art one-shot Florida. We conduct a thorough investigation under provable privacy budgets and propose a novel solution, Fourier Magnitude Filtering, to boost the efficacy of generated data for global model training. We believe our work will inspire the community and foster further research in this direction to improve one-shot Florida with generative models. Let's delve deeper into these aspects in the following slides. Moving forward, let's delve deeper into the technical aspects of our research. On the screen, you can see a qualitative comparison of original training samples and generated samples under a privacy guarantee of E=50. This comparison demonstrates that our approach does not result in blatant memorization, thus ensuring privacy. Our research is primarily focused on two key areas. Firstly, we are exploring the potential of diffusion models for one-shot federated learning. Diffusion models have shown promise in terms of sample quality and diversity, which are crucial for the performance of the trained global model with synthetic data. Secondly, we are studying privacy in state-of-the-art one-shot federated learning. We are conducting a thorough investigation under provable privacy budgets and addressing memorization concerns. Our aim is to inspire the community and foster further research in this direction to improve one-shot federated learning with generative models. Stay tuned as we delve into the specifics of our approach in the upcoming slides. Moving on to our proposed research, let's delve into the FedDiff approach. FedDiff is a novel method that harnesses the power of diffusion models, or DMs, in one-shot federated learning, or Florida. This is a pioneering effort in the field, and we're excited to share our findings with you. The operation of FedDiff is quite unique. It generates synthetic data from models trained on client devices, which is then used for global training. This approach allows us to accommodate the diversity of different systems, making FedDiff a versatile tool in one-shot Florida. Now, let's take a look at the figure on this slide. It provides a qualitative comparison of original training samples and generated samples under a privacy guarantee. As you can see, there's no blatant memorization, which underscores the robust privacy measures in our approach. This is a significant achievement in ensuring privacy in Florida. In summary, FedDiff is an innovative approach that leverages the strengths of DMs, provides a solution for system diversity, and ensures privacy in one-shot Florida. We believe this method will inspire further research in this direction. In this slide, we delve into a key aspect of our research: Fourier Magnitude Filtering. This technique is our answer to enhancing performance under challenging differential privacy conditions. Now, you might wonder, how does it work? Well, it's quite straightforward. We focus on eliminating low-quality samples. This, in turn, boosts the efficacy of the data generated for global model training. Now, if you look at the figure, you'll see a qualitative comparison of original training samples and generated samples under a privacy guarantee of E=50. The comparison clearly shows no blatant memorization, which underscores the robust privacy measures in our approach. In essence, Fourier magnitude filtering is a simple yet effective way to improve the quality of our data and, consequently, the performance of our model. Moving on to the technical details of our proposed method, FedDiff. As you can see in the figure, we've compared original training samples with generated samples under a privacy guarantee of E=50. The results show no blatant memorization, which underscores the robust privacy measures in our approach. FedDiff operates within a one-shot setting, which significantly reduces the chance of eavesdropping. We've tested our method using the CIFAR10 dataset, a popular benchmark in the field. The effectiveness of FedDiff is evaluated based on two key factors: the quality of the generated data and its usefulness for global model training. This dual evaluation ensures that our method not only generates high-quality data, but also contributes effectively to the training of the global model. In the next slides, we will delve deeper into the results and performance comparisons. Stay tuned. Begin a frame. Frame title: Innovative Solutions and Resource Efficiency. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC. Task_execution extracted _paper data 2405.01494v1 figures 2405.01494v1 figure 5:1.png captiona tinea comparison of accuracy, flops, and parameter count for each method on a single client. FedDiff consistently attains heightened accuracy levels while maintaining reasonable resource demands. End a figure. Begin itemize. Item slide 6. Addressing challenges. Begin itemize. Item solution. We propose Fourier magnitude filtering to enhance performance under harsh DP conditions by eliminating low-quality samples. Item efficiency. FedDiff delivers superior accuracy with comparable computational resources to other methods, even on hardware with modest computational capabilities. Item practicality. Training diffusion models within the FedDiff framework is as straightforward as conventional methodologies, making it a viable option for Florida. End itemize, end frame, On this slide, we delve into the key results of our research. We introduce FedDiff, a novel approach that leverages diffusion models for one-shot federated learning. Our findings indicate that FedDiff not only enhances the overall performance of one-shot Florida, but also effectively addresses heterogeneity across diverse settings. However, we also found that under differential privacy constraints, there's room for improvement in the quality and effectiveness of the generated data for global model training. This is an area we're actively exploring. The figure you see here provides an overview of the FedDiff approach. It begins with training a class-conditioned diffusion model on local data at the clients. After training, these local models are gathered by the server to generate data that forms the global training dataset. The global model is then trained on the synthetic dataset. Our work represents a pioneering effort in using diffusion models for one-shot Florida, opening up new avenues for further research in this field. Let's delve deeper into the technical results of our study. As you can see in this figure, our FedDiff approach for one-shot federated learning begins with training a class-conditioned diffusion model on local data at the clients. The local diffusion models are then gathered by the server, where they are used to generate data that forms the global training data. The global model is then trained on this synthetic dataset. Now, what are the implications of these results? Firstly, our findings suggest that diffusion models can be effectively used in one-shot Florida, opening up new avenues for research in this area. Secondly, the success of FedDiff in handling diverse settings suggests that it could be a viable solution for real-world Florida systems with high heterogeneity. Lastly, the limitations under DP constraints highlight the need for further research to improve the quality of generated data while maintaining privacy. These are exciting times, and we look forward to seeing how these findings will shape the future of one-shot Florida. Begin a frame. Frame title a diffusion models for federated learning. Begin itemize. Item, we explored the integration of generative models in one-shot Florida, focusing on diffusion models DMs due to their high sample quality and diversity. Item, DMs simplify the optimization task by learning a Markov process to reverse a fixed forward process, making them potentially advantageous in the challenging Florida environment. Item, we also address the critical importance of privacy in Florida and how training with differential privacy, DP, can ensure this. Item, our research led to the development of FedDiff, a method that leverages the strengths of DMs in one-shot Florida. Item, we also introduced Fourier Magnitude Filtering, a solution to enhance the efficacy of generated data for global model training by eliminating low-quality samples under harsh DP conditions. End itemize, end frame,